Hi everyone, and I hope you are excited to start learning about neurophysiology. Okay, now please don't be scared about neurophysiology. It's actually not too bad, but it's something that we need to learn to understand how neurons work. Okay, so let's get cracking. Now before we start, I want to make sure you understand that topic 5 part 2 I'm going to record in 3 different bits. Okay? Okay, so let's think about our neuron. Here is our neuron. How cute is he, hey? Very cute. Now, what I've done here, I've just cut the neuron and I'm looking at it in cross section. So this is this, okay? Just like you have a pen, and I'm just going to cut it like that, and then I'm looking at it like that, okay? Right, so let's have a look at it. So can you see here that inside my neuron looks different to outside my neuron? So let's have a look and see how different it is. So inside my neuron, how many positive ions are there? I can see I've got 1, 2. How many positive ions do I have outside of my neuron? 1, 2, 3, 4, 5, 6. How many negative ions do I have inside my neuron? 1, 2, 3, 4, 5. How many negative ions do I have outside of my neuron? 1, 2, 3. Okay, so I've got 2 positives and 5 negatives. It's going to give me -3. If I have 6 positives and 3 negatives, I'm going to have a charge of +3. So, the first thing that you need to understand is that the inside of a neuron is more negative than the outside. Okay? Easy peasy. So, this difference, okay, this difference between the inside and the outside of my neuron is called the electrical potential. Okay? So, when we talk about neurons, we're actually talking about charges moving. Okay? So I'm going to do a very highly technical animation. So here we go. Say I've got this charge, it will move. And this charge will move. I have to use 2 arrow keys now. There. So that is what electricity is the flow of ions. Okay? Now, a neuron, we know it's more negative on the inside. This number just represents how negative it is compared to the outside. That's all that means. Right, so we know that neurons are more negative on the inside compared to the outside. Okay, so let's give these ions names. Okay, so some of the positive ones can be sodium and calcium. Okay, and some of the negative ones we have here chloride. Okay, now chlorine is when it hasn't lost an electron. Chloride is when it has lost an electron or has become an ion. Anyway, so can you see that these positives and negatives, they're not all the same. They are made up of different atoms. So let's have a look and see inside versus outside of our neuron. Look at at this. Let's have a look at inside our neuron. We've got potassium, sodium, calcium, chloride, and this thing called A. Now this thing called A just represents proteins that have a negative charge. So which ones are the cations inside our neuron? Okay, so cations, remember, are positively charged. So let me just get my drawing thing here. Let's draw a circle around the positive ions inside our neuron. That one's positive, that one's positive, that one's positive. What about the positive ions outside of our neuron? There you go. Right. Now let's have a look at the negative ions inside our neuron. The negative ones are this one, and the negative ions outside of our neuron is this one. Okay, so we know that we have cations and anions inside and outside of our neuron, and they all are different. Okay? But what you need to remember, that when I add all of these up and compare them to all of these all added up, the inside is still more negative compared to the outside. Okay? That's a major point. Okay. These next few slides go through that in a little bit more detail, but I've summarized it in a very simple form so you can understand. Just shows you what sodium is doing, what potassium is doing, what the protein molecules are doing, and what chloride is doing, and the fact that we end up with a cell sitting at -70. That's essentially what that is kind of illustrating. The other thing that we need to think about is that there is also something called the protein sodium-potassium pump. Now we're going to look at that guy very closely in a minute. Can you see for now that the sodium-potassium pump is a protein? Here is our plasma membrane, and it uses ATP, so it's active transport. Okay, so let's think about this in a little bit more deeply. Like, how does it all work together? Okay. All right, so we know that there are cations and anions inside and outside of the neuron. What I want to do is I want to focus on two very, very important cations. They are sodium and potassium. They're the only ones we want to focus on moving forward, okay, for this section. So sodium and potassium both have a positive charge. So the sodium ones here are the red ones, and the potassium ions here are the blue ones. What can you tell me just by looking at this already about the difference between the two? Right, so the difference is that you have more sodium sitting on the outside of the neuron compared to inside, and you have more potassium sitting on the inside of the neuron compared to the outside. Okay, check. Very, very good. All right, so we know we have more sodium sitting on the outside, but did you know that there are proteins called sodium leaky channels? Now these guys are a tube, and they only allow sodium through. Okay, so what happens is that these sodium ions, they go in through here and sneak in. Okay, So there is the very first protein that I want you to meet. The protein is called the sodium leaky channel. It only lets sodium through and sodium sneaks in. Okay? The other channel that we need to think about is this guy here. Now this guy is called the potassium leaky channel. Let's pop him on. We have more potassium ones than we do sodium ones. I think the ratio is about 50:1, but don't worry too much about that. Now these little guys, they are a protein and they are a tube. And they only allow potassium through. So what ends up happening is that all of my potassium ions, they go, see you later. Now, what do you think will happen over time? Over time, what happens is all the sodium will eventually come in and be equal on both sides, and all the potassium will eventually leak out and be equal on both sides. So we don't want that to happen. So that is why we have something called a sodium-potassium pump. Let me put my channels back in here. It's my sodium leaky and my potassium leak. Ooh, made him huge, didn't I? Highly technical animations here, I know, right? You're impressed? Put them back in. So we have something called the sodium-potassium pump. So sodium is always wanting to sneak in, and it does. Potassium always wants to leak out, and it does. So we need this guy here. Okay? Now this guy looks like that, but I'm just doing it very simple. What it does, it's responsible for grabbing a sodium and chucking it out, and grabbing a potassium and putting it back into the cell. That is his job. Okay? Let me just put him somewhere so I can show you what he does. Okay? So it does this. Oh, sorry, this thing's not working. I don't think. So the sodium-potassium pump grabs a sodium from inside because it snuck in, grabs the potassium from outside because it snuck out, and goes flip, voila, and then this guy can go out here and this guy can go out here. Now the sodium-potassium pump does that day in, day out, all day, every day, and it's the thing that is keeping you alive. Okay, so that is the sodium-potassium pump. Now this thing here, where we have sodium leaking in, potassium leaking out, and the pump going to oppose that, that whole thing, that what's happening there, that is called the resting membrane potential. That is the resting membrane potential. That is what the cell does when it's resting. Yeah? Sodium in, potassium out, pump to fix it. That is its resting activity. All right? Now, what I want to do is look at what happens with local potentials. I think I might stop the video there because I really want you need to really understand the resting membrane potential, and then once you've really understood that, then we'll move on to the next one. I'll stop it there.